at McGill in the Hydrogen Embrittlement Facility, and we are here with Dr. Brahimi. He's going to tell us a little about what equipment is here in the lab, and also some questions regarding the story of how he got here and what is he doing with his different positions. So thank you for doing this interview with us. Could we start with this equipment? What is it? What does it do?
Sure. This is a unique piece of equipment that we've designed and built here at McGill through our facility, through our different funding sources. It's called a thermal desorption spectrometer. And basically what it is, it's an apparatus to help us measure hydrogen in a bulk sample. So if we have a bulk sample, and I don't know if I have one laying around somewhere, but imagine it's a screw or a specimen, a test specimen, so it's a bulk material. And what we do is, the principle of the machine is that we heat it up, and we heat it up in a very high vacuum to be able to extract hydrogen from the material, and then we measure the hydrogen. In fact, we extract other things as well, but we isolate the hydrogen, and so it tells us how much hydrogen is residing inside the material to some extent, and it tells us what the state of the hydrogen of the material is. For example, is it in a trap site? Is it in a diffusible state? So the amount of temperature it takes to get it to move tells us, where it's sitting in the material. The reason why we have, the sophisticated chamber is in order for us to be able to detect the hydrogen, we have to create a very high vacuum. So we're talking about 10 to the minus 8 torr vacuum. So we have these thermal diffusion pumps and mechanical pumps that are designed to pump down the chamber. And we have these valves here that shut off the system or keep it open so that the stream is flowing. So we pump out the system, put the sample in there, heat it up, and as we're heating it up, there's a stream flow that goes through a mass spectrometer, and the mass spectrometer detects the elements, particularly the hydrogen, and gives us the hydrogen concentration in atoms and in molecules, and we can convolute that. And depending on the temperature at which we heat it, we can tell, we see that more hydrogen comes off if we heat it more, and so the temperature correlates with the energy of the trap site, so we can establish how much hydrogen is coming out of it. Now, why does this matter? Because hydrogen in high-strength steel in particular causes it to become brittle when the steel is under stress. And we can do a lot of mechanical testing to see how much strength or ductility the material is losing, but to be able to correlate that with the actual amount of hydrogen, we need apparatus that helps us quantify the hydrogen. That's what the TDS does for us. So this is what we call a stress corrosion cracking tensile frame. So in this case, we will put a sample inside this tensile frame. So for all intents and purposes, it looks exactly like a tensile tester. That's what it is. But at the same time, it has what we call an environmental chamber. So this chamber over here will be filled with sodium chloride solution, and it's hooked up to a potentiostat, which is over there. And through that potentiostat, we can impose a potential or impose a current, and that current essentially generates hydrogen because it's creating an electrolytic cell. So it generates hydrogen at the surface of the sample, and we can basically pump hydrogen into the material as the sample is being tested. So as it's being strained, it's being absorbed, it's absorbing hydrogen. And so then we can see how the material performs in various conditions without hydrogen, with a little bit of hydrogen, with a lot of hydrogen, and then we can then determine how susceptible that material is. So if we're designing, for example, new materials, we would use this type of testing to see whether the new material is responding better to those concentrations of hydrogen.
What's the maximum load?
This machine has a 72 kilonewton load, which in my world is not a lot, but for a lab is a lot. So effectively, we can test a sample of about a 1/4 inch diameter that has a strength of
2600 megapascal, which is very good.
And you're planning to use it mainly for high strength steels?
So that's an excellent question. We have other equipment that we use for high strength steels. This particular design where we're doing the testing in tension allows us to test softer materials. So still high strength, but not ultra high strength. So not the type of materials that would be used for landing gear, but the material that would be used for example, for your typical bolt. And so by doing it in tension, because the other equipment that we use does the tests in bending, by doing it in tension, we can measure loss of ductility, which is another effect of hydrogen embrittlement. So there's loss of strength and loss of ductility. They're both phenomena of hydrogen embrittlement. So the first thing is I'm a big believer in visualization. My background is from sports and athletics, and to succeed, you have to visualize yourself succeeding. So it's important to visualize, to imagine where do I see myself in 5 years and 10 years time, and that image kind of guides your way. So that's the first thing, is to visualize, to have an image, to have an ambition. The second is don't be picky. Start out, whatever direction you're in, start out and learn and learn and learn and really want to do well, and that's going to open the doors that you want. Eventually you'll follow the path that that vision is guiding you on, but to be able to follow that path, you have to perform, because now you're being hired by a company to do a job, and they want you to perform. The better you perform, the better your prospects are for going in the direction you want to eventually go. So those are my two advice. Have a vision, and then roll up your sleeves and work hard and learn as much as you can, especially at the beginning, because you have less responsibility at the beginning, and you have time to learn.